Good evening, everybody. It's nice to see a few participants again tonight, and a very warm welcome to you all on behalf of the Scottish Centre of the Royal Met Society. My name is Gary Johnston, and I'm the Vice President of Scotland, and it is really nice tonight to introduce an old friend to speak to you. But just before I introduce Dr. Shona Mackie, I would just ask you to read the slides that are coming up. Some really interesting stuff happening within RMET. And I would, of course, encourage you all to join RMET. It's a wonderful organisation. It's not only for professionals and academics. Anyone's free to join, anyone's interested in the weather. There's a lot happening, and it's certainly a very worthwhile organisation. The talk tonight will follow the same format, that our speaker will speak for about 3/4 of an hour, 15 minutes, and there'll be a chance afterwards to ask any questions. When we ask the questions, they'll be up on the board. I would ask you to put on the whiteboard any questions as early as possible. If you are going to refer to any slides that Shona needs to refer back to, please put the number of the slide or the name of the slide up as well. After the talk is finished, with the permission of the speaker and the Royal Met Society, we do publish these talks, so you can get access to them again afterwards. So, in saying that, again, a very good welcome to an old friend, and I say that because it was really after I took an interest and finished an Open University course on meteorology that I joined RMETS, and just at that particular time, Shona, who was a member of the Scottish Centre in Edinburgh, asked if she could start up a group in Inverness. She moved to Inverness with her husband David, and they started the group, and I was asked if I would volunteer to help, which I did. So really being on the Scottish Centre is really down to Shona, and she has, with her job, taken her to various parts of the world now, and she's actually coming to us from Bergen tonight, and it's really nice to see you. So I'm just going to hand straight over to Dr. Shona Mackie from the University of Otago, and her talk tonight is how climate models deal with ice around Antarctica. So over to you, Shona.
Okay, well, thank you very much for that introduction, and for everybody else for tuning in. It's really nice having had some part in setting up these talks to actually be here talking about my own work. That's quite nice. So thank you very much for tuning in. As Gary said, I left Scotland, I think, just over 3 years ago now, and I left to go to New Zealand to do some research with climate models. And this talk is going to be about some of the things that I worked on and some of the things that I found out. So, if I can work the slides. Yes, so I'm going to start off, I'm going to sort of give a really sort of brief overview about how climate models work and what they do, and why New Zealand, of all places, decided that they wanted to get involved in this and start doing climate modelling work. And that's going to lead me on to talking about the Southern Ocean and ice around Antarctica, which should lead in quite nicely to letting me talk about some of the work that I did. And I'd like to just briefly talk about 2 projects that I worked on while I was in New Zealand. And one of them was looking at around the coast of Antarctica, where we've got a lot of ice melting into the ocean, and looking at things that are going on there and some of the implications of that for our climate model calculations, and therefore for our climate projections for the future, I guess. And then I want to talk about the other project I want to talk about is looking at sea ice. This is when the surface of the ocean freezes. And I want to talk a little bit about that, why it matters how the surface of the ocean freezes away down in Antarctica. Why should we care about it? And then some work that I did to try and represent it better in climate models and what difference that might make to what we can project for future climate. So to start up, I'll go over water climate models. So we can think of a climate model as a 3D mesh that covers the whole world from the top of the atmosphere to the bottom of the ocean. And these 3D grid cells each of them holds a lot of information that describes the physical state of that grid cell. So for example, if we've got an ocean grid cell, it'll hold information like the temperature of the water, how salty it is, so the salinity, what direction it's flowing in, how fast it's flowing. And it'll also hold information about things like how much heat is being transferred from that grid cell to its neighbours, both next to it and above it and below it. So a climate model is basically that's what we've got. We've got all this information, and when we run a climate model, what we're doing is updating the information in each of these grid cells. And we try to do that, or we need to do that really, frequently enough to represent and capture how frequently this information is updated in the real world. So typically, we need to update these grid cells more frequently than once an hour. So it's a great tool to have. It's kind of like a virtual laboratory, a climate model. You can do things like make a change to one piece of information and see how other pieces of information change, or make a change somewhere on the globe and see where you see other things changing in response. And that's sort of what we do looking at sensitivities, and that tells us how things are related to each other and how processes can affect other processes in sometimes unexpected ways. And that's really interesting, and we can do a lot of cool work. And then the other thing that climate models are used for, which is perhaps what most people think of when they think of a climate model, is we can prescribe a scenario of future greenhouse gas emissions. And that's essentially prescribing a series of changes to the information held in the grid cells. And then we can run that through our calculations, and we can update the model in response to these changes. And then we can say, well, what does the climate look like at the end? And that's what we do when we calculate projections for future climate. So that's a lot of grid cells. And I said that we typically need to update the information in them more than once an hour. And when we look at climate, we're generally looking for hundreds of years. So that's an awful lot of data and an awful lot of calculations, which means that we need huge computing resources if we want to do a good job. And this is quite important. It's not just a technical thing, because nobody has infinite computing resources. It's not possible. So this means that there will always be things that have to be simplified. There will always be details that have to be left out. The key is, which details do we leave out? What is important? And what we try to do is we try to focus on what matters for climate. So we try to include all the details that we think are going to be really important and impact on the climate that we experience. The problem is that the processes that are really important and impact really strongly on the climate that we might experience in Edinburgh or in Scotland or Northern Europe might not be the same processes that are really important for climate somewhere else, like New Zealand. So this brings me to why New Zealand decided to get involved in climate modelling. Not every country has the resources or the inclination, to be honest, to get involved in climate modelling. It's a huge expense. And we've already got a lot of really good models out there that we can all use. So New Zealand decided they wanted to get on board because, well, every year, well, not every year, sorry, but every few years, the modelling centres around the world, different international groups who have a climate model, get together and we compare our models. And this is what we call CMIP, a model intercomparison project. And we compare the models to each other, but we also use them to simulate the recent climate, so the recent past, because then we know for the recent past what the climate actually was. And the idea is that we can compare what the models say the recent climate was and what we actually experienced. And that gives us an idea of how well the models are doing. Now, it doesn't necessarily mean if a model can represent the recent past very accurately that it will represent the future very accurately, because different processes may become important as the climate changes. But short of having a time machine, we're a bit stuck for much else to do. So this is the best sort of handle we have on how well the models are doing. And when the fifth iteration of this project came about, so the fifth time that we did this comparison between all the models, we noticed that there were huge problems in the way the Southern Ocean and things around Antarctica were represented in the model. So I don't think I can use my cursor on the slides. I don't think you can see it. But the Southern Ocean is basically the ocean at the bottom of the Earth. So everything sort of below the land masses down there. And that's the Southern Ocean. And climate models weren't representing at least the recent climate very well in the Southern Ocean, and they were doing particularly badly with representing recent changes in sea ice around Antarctica. So sea ice is where the surface of the ocean has frozen solid. And in the figure there, where we've got the colour red, that means the entire grid cell is solid ice at the surface. So it means the ocean surface is completely covered in ice. Where it's blue, there's no ice at all. So if we look at the white circle, that's just to show everyone where New Zealand is. And you can see why New Zealand started to get a bit worried. Because if climate projections aren't very reliable for the Southern Ocean and things around Antarctica, well, perhaps they're not going to be that reliable for New Zealand, or at least it's something that New Zealand felt they should be looking at. So that was one reason why New Zealand wanted to get involved, is really to take a bit more ownership of their own climate projections and be sure that they understood what they were calculating and what the assumptions behind that were, and see whether they could trust them or not, or how far they could trust them. And the other reason that New Zealand wanted to get involved, and it makes a lot of sense really, is they may not have had a great tradition historically in getting involved in big modelling projects like climate modelling, but they do have a very, very strong tradition of making observations in the Southern Ocean and of ice around Antarctica. And they have a really good understanding of processes that go on there and how things interact and what's going on. And if you have a really good understanding of something, and there are models out there that aren't doing very well at representing it, it makes sense that you get involved and try and make those models better, use your understanding to improve those models. So that's why New Zealand decided to get involved, which I was asked about a lot when I first started, because it's quite a big step. It's a big investment to suddenly decide to start climate modelling. So now I mentioned that sea ice is quite important, and this video, I think we're just going to see, is just to show you, this shows you the area of the ocean that's covered in ice around Antarctica and around the Arctic. It's a time series from 1979 to 2016, and it's just showing you the sea ice coverage in September every year, which is when we have the most amount of sea ice around in Antarctica and the least around the Arctic, because obviously the seasons are flipped. And the point I want to make here is that they're very different environments. The Antarctic is this huge landmass surrounded by ocean, whereas the Arctic is an ocean that's pretty much surrounded by land. So we've got very different environments, and that means that different processes are likely to be important. So although we've got the ocean freezing solid in both places, or the surface of the ocean freezing solid in both places, there may be different processes driving that. And if we remember that climate models, we're trying to focus on processes that are important and affect our climate. And if most climate models are developed in the Northern Hemisphere, it's likely that we're going to be focused more on things that happen in the Arctic. So I want to talk a little bit about processes in the Antarctic that are important to sea ice in the Antarctic and why they matter. But first I'll have to step back a bit and explain what those processes are before I can try and convince you that they matter or that climate models struggle with them. So this is a schematic that I thought would be quite good for describing one of the things that happens around Antarctica. So on the continent, on the landmass itself, we've got it's mostly covered in ice, and that ice mass is growing all the time as we have snowfall. And the more snow we have, the more ice we have. So we're getting more and more ice all the time. But we're also losing ice all the time, because that ice on the continent flows out to the coast. So it flows northwards out to the coast. And when it reaches the coast, it doesn't just drop off into the ocean. It makes these tongues that float out. And these are what we call ice shelves. And the grounding line that I've marked there with the dashed line, the grounding line is what we call where the ice shelf leaves the ground, if you like, and this tongue begins that floats. It's different from sea ice, which is just the surface of the ocean freezing. This is ice that's flowed off the continent. And the ocean water is warmer than this ice. So this ice shelf is melting all the time. It's being replenished all the time as ice flows from the continent, but it's also melting all the time into the ocean. And there are icebergs calving off it. So when we say icebergs calving, we just mean breaking off. So we've got bits of ice, big chunks of ice breaking off the ice shelf all the time. And they float away according to ocean surface currents and winds. and they then also melt into the ocean. So the question is, are we losing ice more quickly than we're gaining it, or are we gaining ice and we're growing the ice mass more quickly than we're losing it? If we're in a sort of state of balance where we're growing as much as we're shrinking, so things aren't really changing, we call that mass balance. And some climate models assume that's what's happening. And other climate models assume that the loss rate, so the rate at which we're losing this ice mass from the continent, either through ice shelf melt or through icebergs that are then also melting but further away from the coast, that loss rate is constant. So is that the case? Well, probably not. There's a lot of local variations. When you look around the coast of Antarctica, there's a lot of different things going on. But glaciology tells us that on the whole, we are losing mass more quickly than we're gaining it. And it's the rate of mass loss is increasing. But this isn't represented in our climate models. As I said, climate models generally assume that this rate of mass loss is constant, and we don't think it is. But the question is, but does that matter? Remember, we're always interested in, is it going to make a difference? It's very interesting. There's not a lot of point in putting a lot of effort into it and making the model more complicated than it needs to be if it's not actually going to impact anything. So does it matter? Is it something we need to worry about? New Zealand are starting with their climate model. They're not starting from scratch. They're starting with a copy of the UK's climate model. And the UK model assumes that this mass loss rate is constant. So New Zealand are wondering, well, should we worry about that? Should we just go with that, or should we change it? Should we look at putting something more accurate in there? So the first question before you say, well, what would we put in that's more accurate? The first thing to ask is, well, does it make a difference? Is it worth looking into further anyway? So that was what one of the projects that I worked on was doing. So what I did was I ran a climate model, so the New Zealand climate model, for 100 years. So I keep using the cursor and forgetting you can't see. So along the x-axis here, we've got 100 years. So I ran a model for 100 years. And up the y-axis, we've got the rate at which Antarctica is losing ice mass. And where it starts there at year 0, that's the rate that all our climate projections, at least from the UK model, assume that number is constant, and that is the number that is fixed. That's the rate at which we're losing mass. And what we wanted to see is, well, what if that number is allowed to increase? Then will it affect anything? Will it change what the climate looks like in the model? Will it change anything anywhere else? So we ran a 100-year simulation, allowing it to increase so that after 100 years, we've increased the rate of mass loss by a factor of 10. Now, it's not necessarily a realistic increase. Some people might say it is. There is some work that suggested it's in the ballpark, but I'm not confident saying that's a realistic increase. At this point, all we want to know is, does it make any difference? Do we care, basically, that we're not including this increasing mass loss? Does it matter if we assume that it's constant? So we did this experiment and we compared the results to letting the rate increase and to keeping it constant. And we didn't change anything else because we've got so many interactions in the climate system going on. It's a really, really complex system. And we didn't want anything else to be, we wanted to know that any changes that we saw were directly attributable to this increase in the mass loss rate. So we didn't increase greenhouse gas forcings, we didn't increase carbon dioxide, we didn't increase anything. The only thing that's increasing and changing in this experiment is the rate of mass loss. So did we see any difference? Well, yeah, we saw quite a big impact on the sea ice around Antarctica. So this shows you, this is the change in volume. This is the additional sea ice that we created. So another 26,000 cubic kilometers of ocean froze when we allowed the rate of mass loss to increase from Antarctica. Sorry, I say this is the average over the final 30 years of that 100-year experiment. So we saw a massive change in sea ice, a lot more of it, and it was a lot thicker. That's not very surprising. When we increase the mass loss rate from Antarctica, we're basically increasing the amount of fresh meltwater that is entering the salty ocean, either through this ice shelf melt or through the icebergs, which break off, but ultimately they also melt and constitute a freshwater flux into the salty ocean. Fresh water is less dense than salty water, so it sits at the surface of the ocean above the salty water. And that means that it freezes far more readily than salty water would. Because salty water, the surface of the ocean in the absence of fresh water, the surface of the ocean will be cooled by the atmosphere. Around Antarctica, the atmosphere is almost always much colder than the ocean. So the ocean's always losing heat to the atmosphere. The atmosphere has this cooling effect on it. So warm water generally, well, relatively speaking, warm water sits at the surface, is cooled by the atmosphere. If that water is salty, it becomes more dense and it sinks, which means it's replaced by more water, which is, we call it upwelling, is pulled up to replace it, which is warm, which then sits at the surface and is cooled and then sinks. So you have this constant replenishing of the water. So it takes a long, or it can take a long time to freeze the surface. Whereas fresh water just sits there, getting colder and colder and colder. So it's subjected to more cooling. It's much quicker to freeze it. It's also got a higher freeze melt temperature than salty water, so it's easier to freeze it anyway. So yeah, it's not surprising. Yeah, we get a lot more sea ice. Great. Does that matter? Why would we care about sea ice? Well, I'm obviously a little bit biased, but I would say yes, it does matter. And I'd say firstly, it matters for what we call the albedo effect. So the albedo is the proportion of solar radiation that is reflected back to space rather than being absorbed by the Earth, in this case by the ocean. So sea ice is a lot more reflective than the dark ocean surface. If it's just covered in water, if it's just got a water surface, it will absorb a lot more radiation than if you've covered that surface in ice. A lot more of it will be reflected back to space. So we're changing the amount of solar energy that we're receiving if we change the amount of sea ice that we've got on the ocean. We're also, when we put sea ice on the ocean, we're also introducing a physical barrier between the ocean and the atmosphere. And as I mentioned, the atmosphere is almost always a lot colder than the ocean around Antarctica. So there's a lot of heat exchange goes on. That's how the ocean loses its heat to the atmosphere around Antarctica. We inhibit that exchange if we put sea ice in the way. And similarly, things like carbon dioxide exchange are inhibited, and that's going to affect budgets. So heat budgets, energy budgets, and so on in the ocean and in the atmosphere. And then there are salinity effects that I'm going to talk about a little bit more later, but salinity effects can be really important for ocean circulation, and I'll come to that a bit later. So this increase in sea ice, when we increase the rate of mass loss from Antarctica, is the opposite of what is projected under global warming projections, so climate projections for the future. So climate projections for the future generally assume, well, in the model that we're looking at, they assume a constant rate of mass loss from Antarctica. And the world warms as greenhouse gases increase, and we project that sea ice will decline. So we thought, well, actually, they're not taking account of this extra meltwater coming into the ocean. So maybe they're exaggerating in these climate projections how much sea ice we're actually going to lose. So we thought it would be interesting to compare our experiment to an experiment with the same model where the rate of mass loss is constant, so we don't have these extra freshwater fluxes, but we allow carbon dioxide to increase by 1% every year. So it's an idealized experiment. It's not a real life experiment. It's not how much we think carbon dioxide would increase by, and actually, crucially, nothing else is increasing, just the carbon dioxide. It's an idealized experiment, but it's just to see how these two things compare. And it looks like, when we look at the results here, the carbon dioxide experiment on the bottom there, we can see we get the exact opposite effect. Well, not the exact, we get the opposite effect. We get less sea ice and we get thinning. As we'd expect, we've got a warmer world, we have less sea ice. But we thought it'd be quite cool to see what happens if you have these things happening at the same time. So we did another experiment, where we allowed the mass loss from Antarctica to increase, just as in our first experiment. But at the same time, we allowed carbon dioxide to increase by 1% every year. And then we saw that, yeah, they pretty much did cancel each other out. We got very small changes, and they really did offset each other. Now, I really need to stress here, these numbers are pretty meaningless. These are idealized experiments. So the rate at which we increase the mass loss from Antarctica was pretty big, and it was to see what would happen. And similarly, the 1% carbon dioxide increase is to see what happens, to see what the response is, to see if there is a response to these two things. So we can't say that they would counter each other. It would obviously depend how big the forcing was, either how much the increase in CO2 was, and also how much the increase in the melt fluxes was. But what we can say from this is it is perhaps something that we need to think about, because it is perhaps a mechanism that could counter some of the projected decline in sea ice. Now, I mentioned salinity and ocean circulation, and that's something I'd like to talk about a little bit more, because if we can change the amount of sea ice in our climate projections, we may be changing the representation of ocean circulation. Maybe it may affect what we calculate for ocean circulation. So the way that this works is when sea ice freezes, it can affect ocean circulation, because we've got salty water freezing, and it's freezing to form ice that is relatively fresh. So as the salty water freezes, the salt is squeezed out, making the water round about much saltier. And because that water is much saltier, it's much denser, which means it sinks. And that's pretty important. So I'm just going to explain in a second why that's important. But first, I'm going to explain why ocean circulation is important, and why we're worried about it, and why that process of that dense water creation might be something that we really should be concerned about. So the ocean is not just a massive heat sink. It is a massive heat sink, but it's not just a massive heat sink. It's also the way that main ways that heat is distributed around the planet. So this schematic here, this little picture, just sort of shows you how the oceans of the world are connected. And it shows you the main pathway by which water travels around the world. And the red is warm water, and the blue is cold water. And we can see that really heat is being, if we change this circulation, we will change the distribution of heat around the Earth. And that's really important, I think, for climate everywhere. So yeah, how can sea ice and this dense water that it creates, how can this be possibly affecting that? Well, this is what we were thinking. So as we make the sea ice and we squeeze that salt out and we make this dense water, and this dense water sinks, well, in some places, and it doesn't happen everywhere around Antarctica, but in some places, this dense water is dense enough that it sinks right to the bottom of the ocean. And we call this Antarctic bottom water. It's the coldest, saltiest water, I think, in the ocean. So we call this Antarctic bottom water. And it's what drives the bottom half of this schematic that I've shown here. The bottom half of this ocean circulation is pretty much one of the main drivers for it, is this bottom water formation. So if we change the amount of sea ice we're producing, then we're changing the amount of salt we're squeezing out, we're changing the amount of denser water that we're making, we're changing potentially the amount of bottom water we're making. So possibly we're going to be changing ocean circulation. Under a warming climate scenario, we anticipate that there will be less bottom water produced, partly because there will be less sea ice. So if we're offsetting the decline in sea ice by accounting for this increased mass loss from Antarctica, so if we're saying, okay, we're not going to lose as much sea ice as we thought, well, then maybe we're not going to lose as much bottom water as we thought. And so maybe the slowdown that we're talking about and that people are sort of predicting for ocean circulation, maybe that's being exaggerated in our climate projections. Maybe we don't need to worry about it quite so much. So we thought that was something worth looking at. So I'll just talk about the plot first and then try and explain why. So this plot shows you what we found when we looked at this. So on the x-axis, we've got the 100 years that we ran our experiments for. And on the y-axis, we've got a measure of how much of this dense bottom water, this sinking water, how much of it is being produced. And the black line shows you if we don't increase carbon dioxide and we don't increase the rate of mass loss from Antarctica, so everything is just constant, then we can see it does fluctuate, it does vary, it's not a constant thing. There is some variability there, but it's not increasing or decreasing, it's just fluctuating. If we increase carbon dioxide, but we keep the rate at which Antarctica is losing mass constant, so which is the assumption in our climate projections, then we see this grey line. And the grey line shows that we get a decrease in bottom water production. But then we thought about, aha, what if we increase the mass loss from Antarctica at the same time? So we're offsetting the decline in sea ice. Will we then offset this decline in bottom water production? And that's the yellow line there. And we see that actually, no, we don't. If anything, it looks as though possibly, if we were to run the experiment for longer, it looks as though possibly we might get an even stronger reduction. So it looks as though actually this increased mass loss from Antarctica, even though it's giving us more sea ice, somehow it's compounding this effect, this decrease in bottom water production. So we're getting more sea ice, but we're getting less bottom water. So how is that possible? Well, as this mass loss from Antarctica is essentially a freshwater melt flux into the ocean, either from the ice shelf melt or the icebergs. So we've got fresh water going into the ocean. And there's so much of it going in that actually the ocean is getting a lot fresher. So that means that when the ocean freezes to form sea ice, there's a lot less salt to squeeze out. So although the water round about still gets saltier as the salt is squeezed out, it doesn't get salty enough to become dense enough to sink to the bottom of the ocean and form bottom water. So even though we get an increase in sea ice production, we don't get an increase in bottom water production. We don't offset the decrease in bottom water production. And in fact, we might even contribute to it further. So that was pretty interesting to see. And then the last effect that I thought would be interesting to show you would be looking at ocean surface temperature. So this is again looking at the final average over the final 30 years of a 100-year experiment. And we know that as we increase the meltwater around Antarctica entering the ocean, we know that this causes the surface ocean to cool. So we can see that in the plot on the left. In the plot in the middle of the screen, we see what I think everyone's quite familiar with. We see carbon dioxide levels increase and the temperature of the surface ocean, it increases in our model. So we thought, well, these are opposite effects. Maybe they offset each other. Do they offset each other? So we thought we would look at them together and see what happens. And we can see that if we allow the melt fluxes around Antarctica, so there's mass loss from Antarctica to increase and carbon dioxide to increase at the same time, then this is what we see this plot here. It doesn't, the melt fluxes, the extra mass loss from Antarctica doesn't make a huge difference in the Northern Hemisphere at all. But if you look around New Zealand, and remember, New Zealand's interested in what's going to affect New Zealand climate first and foremost. If you look around New Zealand, you see, yeah, we're still getting a warming. The ocean surface is still warming, but it's not nearly as strong. And so this is an example of something that made New Zealand go, yeah, okay, this is something that maybe we can understand other people not having looked at in depth, but maybe this should be more of a priority for us. So that was quite interesting to see. Again, I should stress again that the numbers themselves are meaningless. So we've got a little bit of a net cooling effect we can see coming off Antarctica there. But the actual numbers are meaningless because we've got the two forcings are both idealized forcings. It's just to see what happens and see if there's enough of an effect that it's something we should look at. So I wanted to use that to demonstrate sort of what you can do if you've got your own climate model and the sort of things you can look at and how you can really focus on what's important to you, as New Zealand did. And we found out quite a lot of other effects as well, looking at things around Antarctica, and quite a lot of sensitivities that were quite interesting for New Zealand, but perhaps not really having that much of an effect on things in the Northern Hemisphere. So that was quite nice for New Zealand to justify all the money they'd spent, I suppose. But it was quite interesting, and it's a good demonstration of what you can do with a climate model. But the other thing you can do with a climate model, of course, is once you've discovered things that are important to you, you can make them better, or you can try to make them better. So that's what I want to talk about next, is looking at a project that I did to try and improve something in the model. So sea ice seems to be pretty important to New Zealand. As we showed, it's got all kinds of consequences, and New Zealand's pretty close to sorry, I'm trying to do too many things, but New Zealand is pretty close to the Antarctic relative to the rest of us, and so therefore they're very interested in sea ice. And I've got a video here of, so this is just showing you, hopefully, yeah, a video of sort of year in the life of sea ice around Antarctica. This is going through the year 2016, and it's just showing you how the ice, every year we get massive ice coverage in September, a huge area of the ocean freezes, but it also mostly melts. Almost all of it melts through the year and then has to refreeze again the next year. And this is very different to what happens in the Arctic, where we've got multi-year ice, which is ice that persists from year to year. So although that ice gets thicker every year, we don't have so much new ice forming in open water as we do in Antarctica. And perhaps for that reason, the processes by which new ice forms in open water where there is no sea ice are not very well represented in climate models generally. Interestingly, this process of forming sea ice in open water is becoming more important in the Arctic now as well, because that multi-year ice that persists from year to year is being lost as the climate warms. So this process is becoming more important there too. So how does sea ice form in open water? Well, one way that it forms is from grease ice. And so bear with me, I'm going to try and explain this. So grease ice forms when we have supercooling in the ocean, which can occur through, there are various mechanisms that can give rise to supercooling in the ocean. And supercooling means we've got droplets of water that are colder than the freeze melt temperature of the surrounding ocean. So we've got supercooled water droplets. So they're water, but they're colder than the freeze melt temperature of the surrounding ocean. And these water droplets can freeze to form what we call frazzle crystals. So these small crystals of ice that we call frazzle that rise to the surface. And as they rise to the surface, these ice crystals mix with the ocean water at the surface into this really sort of slushy, soupy layer that isn't solid sea ice, but it's not quite water either. It's this soupy stuff made of about 3/4 water and about 1/4 made of these ice crystals. And this is what we call grease ice. If the surface is warmed by the atmosphere, so if you've got a very hot day, which doesn't really happen in Antarctica, but in the Arctic, you could have the surface warming and the grease ice can then melt away. It may not ever freeze solid. You might get this slushy stuff forming grease ice and then it just disappears, melts away. If you've got a cold atmosphere, then slowly this layer of grease will freeze solid and will solidify to form new sea ice. So that's one of the ways in which new sea ice forms in the atmosphere. While it's in this intermediary stage, this grease ice stage, which is neither solid sea ice nor water, it isn't solid, so it's sort of malleable. So it's subjected to being blown about by the wind and moved about by ocean currents. So it's not a solid layer. It doesn't have a nice even sort of distribution across the water surface necessarily. If there's an edge in the water surface, for example, if we've got some existing ice in the water and the wind may then blow this greasy slushy stuff up against it and it might pile against this edge and therefore not be distributed evenly over the cell. Crucially though, the really important thing, probably the most important thing about it, is that it doesn't freeze straight away. But this is not how we represent it in climate models generally. In climate models, we say these frazzle crystals, when they reach the surface, well, that is sea ice. We just say that's new sea ice. That volume of ice from the supercooling in the ocean, when it gets to the surface, that's new sea ice. There's no time delay. We don't have this intermediary stage of grease, and we don't mix it with the water at the surface. We just freeze it in a thin layer over the surface of the ocean. It can't be moved about by the wind, it's just frozen solid instantly. So, yeah, it's not very realistic, but does it matter? Well, it probably means that in the model, new sea ice forms too thinly and too fast. And that means we're covering up the ocean surface too quickly, which has implications for all the things we've talked about when we've talked about sea ice. So implications for the heat and the carbon dioxide exchange, implications for the albedo, and so on. So this could be quite a big problem. So I set about trying to improve it, working on this work, following on from this work that these guys in Reading had done here. And I'm going to try and explain, hopefully quite simply, what it was that we did. So we took these ice crystals, these frazzle crystals, that when they reach the surface of the ocean, well, we said, first of all, simple case, the ocean surface is already covered in sea ice. Fine. We'll stick these crystals to the underside and say we've got thicker sea ice. Job done, great, let's move on. So that's great. But where we've got open water, what we did was we mixed these frazzle crystals, we mixed these little ice crystals with the water that was there at the surface of the grid cell to make a grease layer. And then if there was sea ice in the grid cell already, if it wasn't all open water, we let this grease layer be distributed like this. So hopefully, I'm not sure if this is displaying properly, but hopefully you can see that we've got a sort of wedge shape of grease ice that's been blown by the wind and by ocean currents against the edge of the sea ice. And some of it is spilled over on the top of the sea ice and some of it's spilled under the sea ice. But crucially, there's some open water behind the grease ice. It's no longer covering all of the water in the grid cell. So we call this herding. So these changes mean that sea ice takes longer to form and it's thicker when it forms because the thick edge of that wedge shape can be as thick as the existing sea ice. It means that leads are just cracks in the sea ice, can stay open for longer. And this hopefully means that all these processes that we've talked about can be more realistic, and therefore we get a more realistic energy budget in our ocean. So I want to show you, just to finish off, with some effects that we saw from this when we implemented it in a model. So this is actually looking at an ensemble of climate model simulations. So that just means that we ran several model runs and we took the average. And that's to account for variability a little bit. And these are using historical forcings, and this is comparing our grease ice scheme, so including this intermediary stage in Greece, with the same model runs without that, using the standard model configuration, the standard way that sea ice forms in the models. And we actually used the model configuration that was used in the model intercomparison, the latest model intercomparison project to do this. And what we saw was that when we implement our grease ice scheme around Antarctica, we get some thickening of the ice around the coast, and we expect that because around the coast of Antarctica there is some multi-year sea ice, so the ice there is thicker. And remember, under this scheme, the way that we make this grease ice means the new sea ice can be as thick as the existing sea ice. So where we've got thicker existing sea ice, we expect thicker new sea ice. So that's not surprising. In the Western Pacific, which is, I always get confused about east and west with Antarctica, but closest to the colour bar in the plot, we see this big increase. And this is a lot of new sea ice, a lot more sea ice that we create when we have this grease ice scheme in there. And that's because when we have this grease ice stage included in the model, we allow the open water to remain open for longer. We're not covering it in ice so quickly. And that means that the ocean can cool more. So we can get a colder ocean and we can make more sea ice. What was a little bit, threw us a little bit and was a bit of a surprise at first was this blue area in the opposite corner of Antarctica there. And we hadn't expected to see this. This is a decline in sea ice. So including this grease ice scheme means we actually get less sea ice in this area. But this is because we've got an area of what we call convection here. So convection is where we have warm water upwelling from the ocean to the surface. And what happens around Antarctica when we've got this warm water upwelling is it's cooled by the atmosphere and it freezes. And then as it freezes, it's blown. We've got really strong northward winds blowing off Antarctica generally. So as this warm water comes up to the surface, it freezes and it's blown north. And then eventually, when it travels far enough north that it meets warmer water, it melts. So when we don't include the grease ice stage of sea ice formation, Then in the model, in the standard model, we'll have this warm water upwelling. It'll freeze to form new solid sea ice, which is transported north and melts. When we include grease ice, then instead of forming sea ice, we have this warm water upwelling, and we form grease ice. And the grease ice is transported north. And actually, a lot of the grease ice is transported far enough north that it melts before it's ever frozen to form new sea ice. So actually, even though it was a bit of a surprise, it is actually, I think, more physically realistic. And then the Arctic, we saw huge effects, but these were much more along the lines of what we were expecting. Much thicker ice, for all the reasons that I talked about, because the existing sea ice in the Arctic is much thicker because we've got more multi-year ice. So the new ice that forms is much thicker. And we can form a lot more of it because areas of open water are remaining open for longer, which means that they're subjected to more, the ocean is subjected to more atmospheric cooling. It loses more heat to the atmosphere, so it gets colder, which means we can produce more sea ice. So we saw this quite massive effect here. And this has been proposed as a mechanism that may provide some healing for Arctic sea ice decline, actually, in the Arctic. It's being talked about at the moment quite a lot here in Norway. And so this is just what I wanted to finish on, really. I wanted to sort of get across that climate models they're really smart. They're really, really clever things, but they cannot be perfect. They're not perfect, but they can't be. It's impossible. They cannot be perfect. No models can be. By definition, models are approximations. But they can be really useful to us so long as we understand them and we understand what they do well and what they don't do well. And I got a couple of quotes from a famous modeler in the 70s, George Box. The quote on the left is pretty well known. All models are wrong, but some are useful. And the quote on the right, I really like. It's less well known, but this is what we were trying to do in New Zealand is, since all models are wrong, we wanted to be alert to what is importantly wrong, because it is inappropriate to be concerned about mice when there are tigers abroad. And I'll just leave you with that. And yeah, some shameless self-publication there, but if anyone really wants to know more about the work that we were doing in New Zealand, then there's some papers there on it. So thanks very much.
Thank you, Shona. That was really interesting, fascinating research. It really is. And great that you got the opportunity to go down and work in South America and study this firsthand. Very exciting. There are lots of applause coming up tonight, and I'd just like to say, you know, it's great to see people from all over the UK, but also welcome to our friends from Brazil, India, and Ireland. A great thing about these virtual talks are that we can get people tuning in from all over the world. There are a couple of questions, but just first, I have one question, Shona. Looking at the ocean circulation models you were looking at and the way it works, and obviously with the bottom water you're talking about, the ice being squeezed out and sinking a lot heavier, as the circulation goes up to the Southern Ocean, is there any evidence that it is affecting the Southern Ocean oscillation and therefore affecting the El Nino effect? Because we have seen it, some pretty wild oscillations there over the last few years.
Probably. I don't know is the answer. Whether Antarctic bottom water would affect the Southern Ocean oscillation and El Nino. I don't know is the answer to that.
Okay, that's fine. A question from David Stevenson, an old colleague of you, an old friend of yours. Just a very interesting question about how the Antarctica is actually defined both in atlas terms and in terms of climate models. When your, as he puts it, your cartoon shows that the ice increases and decreases throughout the seasons.
Yeah, how we define it in atlases, I don't know, but in climate models, not very well is the answer. So we have the cavity under the ice shelf, so the space between the underside of the ice shelf and the seafloor, we don't represent in the model at the moment in its operational format. You can open it up, but the reason that we don't represent it is because the position of that grounding line moves. And we can't allow it to move in the model without basically crashing the model and having huge numerical instabilities. It's kind of a technical challenge of allowing the grounding line to move. So we have actually quite a new parameterization for the cavity. The different models use different parameterizations, but we essentially in our model, in the UK model and in the New Zealand model, the edge of the front of the ice shelf is considered to be a vertical wall, and that's basically the boundary of the ocean. And then what we do, most of the melt from the ice shelf occurs in the real world at the grounding line, and then follows, so at the bottom of the ice shelf, at the deepest part, and follows the underside of the ice shelf up. Some of it sticks back onto it, but most of it follows up, and that's what forms these, one of the ways that you can form these frazzle crystals, because the melt is supercooled because it's fresh, so it's buoyant. So when it melts, it enters the ocean, it rises up. The pressure change obviously makes it become supercooled because the freeze melt temperature of the water around it will change. So that's one of the ways that we form frazzle crystals. But instead of having the cavity, we just have this wall, and we distribute the melt from the ice shelf evenly through the vertical, from the average ice shelf draft for that ice shelf to the ocean floor. Does that answer the question? I don't know.
Yeah, okay. Thanks, Shona. A question from Aaron. I'm not sure I quite understand, but why decrease of bottom water formation start after 30 years, approx in your control experiment?
It shouldn't have done. Let me just go back to the plot. Right, here we are. So after approximately 30 years, oh, you mean when we increase carbon dioxide, in the 1% carbon dioxide experiment, why did we start to see this decrease? Basically, it's a delayed effect. A lot of the effects that we see when we change things in the climate have a lag on them. Carbon dioxide is, it's when we increase the carbon dioxide by 1%, we're increasing it in the atmosphere, and we're looking at an effect in the ocean. So the world is warming, but it's not, we increase the CO2 and simultaneously increase the warming. There's a lag there. So that's what that is. There's a lagged response. Actually, when it comes to the ocean, a lot of responses to things that happen in the atmosphere are quite strongly lagged.
Okay, thanks, Shona. A question from Patricia. From what range of depth do frazzle crystals ascend?
Well, it depends. So as I said, it depends where they're originating from. So if it's from the bottom of an ice shelf, so if it's ice shelf melt, as I was just talking about, then ice shelves, the grounding line, where the ice shelf comes away from the ground, can actually be below sea level, because the weight of the ice on the land has pushed the land down below sea level. So in that case, they come from, depends on how deep the ice shelf goes. I think, I'm not sure, maybe like ice shelves around Antarctica. Oh, I should know that. I'm going to say of the order a kilometre max, I think. But then we get a lot more frazzle crystals forming. A much more common process that gives rise to frazzle crystals is where we've got an area of open water surrounded by sea ice, and we've got really, really strong winds, really cold, really strong winds coming off Antarctica that make the water at the surface really, really, really cold, but also very, very turbulent. And they can actually make the water colder than the freezing temperature, but at the same time mix it down below the surface. And in that case, then they're not very deep, but they then, the super cold water is mixed below the surface and then rises to the surface and forms frazzle crystals. But in that case, it's maybe just a couple of 100 meters max. So yeah, it just depends.
Okay, thank you, Shona. One from Jonathan Smith. With just the chance of ice mass not being constant, are the regional variations around the Antarctica significant for New Zealand?
I would say yes. we looked at quite a few things that I didn't talk about here. One of the things we looked at was changes to what we call the westerly winds. So there's a belt of circumpolar winds around Antarctica that it's just westerly winds that are there. And this belt moves a little bit north and south, but its position determines storms, the storm tracks, the storms that New Zealand experiences mostly, well, a lot of them originate from this belt of winds. And we found that by increasing the amount of sea ice, which follows from increasing the rate of mass loss from Antarctica, we found we actually changed the position of this wind belt. And so that does have implications, quite direct implications for New Zealand climate. But then there's also effects on sea surface temperature, and also sea surface salinity, which I didn't talk about. But really, to get into the detail of what those effects are, you really have to look at more realistic numbers, and you also have to look at, remember, we kept everything else absolutely constant in these experiments, and in the real world we've got emissions increasing all the time, we've got things changing, so you'd have to do more experiments to look at that. You'd also have to look at, we increased this rate of mass loss right around Antarctica by the same amount. And in reality, the rate of mass loss is increasing by more in some places than in others. In some places, it's not increasing at all. So you don't know without doing a little bit more work. And we started to look at it, and you need to do a bit more work to say, well, where is the melt from? Is it the melt from there that's having this effect, or is it the melt from there that's having this effect? So until you can do that kind of tracing, which is really interesting to do, and is something that we were starting to look at, but we didn't look at that so in enough depth to be able to say. But I'd say, yeah, we do get significant effects on New Zealand for sure.
Okay, thank you. My apologies to David Stevenson. He did have a follow-up comment, and sorry, I'm reading these as they're coming up on the board, so apologies, David. I see you've taken it down. Question from Christina, saying good presentation. Global climate models over time, precipitation in Antarctica. Is it possible to improve precipitation using regional climate models in the region?
Possibly. A regional climate model for Antarctica would be verging on bigger than regional, I'd have thought. I think a better way to improve it, well, I guess there's different ways of looking at it. So when I said that they have problems, climate models in general have problems with the Southern Ocean, the temperature of the Southern Ocean was a massive problem that has got a bit better, but is still quite a big problem for climate models. And the main cause of that problem is thought to be the representation of clouds above the Southern Ocean. We don't have nearly as many observations from that part of the world, and certainly when we get to looking over the landmass of Antarctica, we don't have nearly as many observations as we do for the Northern Hemisphere. So we're sort of a bit struggling in the dark, at least relative to the Northern Hemisphere. But it is the atmosphere there that was a bit of a problem. So by trying to improve the atmosphere, yeah, sure, then we would improve precipitation. But I think a more promising and more likely sort of way that this is going to improve, I think, is we're looking at trying to couple a dynamic ice sheet model. And if we could couple a dynamic ice sheet model for Antarctica, then we would be able to let the surface in that, because at the moment it's just a boundary condition. So we don't have anything feeding back to the atmosphere over Antarctica. So over Antarctica, we get a little bit of sublimation. We don't lose all the ice through ice shelves and through the ice shelves. We do get a little bit of sublimation, and around the peninsula, a tiny little bit of surface runoff. But most of the mass loss is at the ice shelves. But we could do precipitation better, I think, if we modelled the ice better and coupled it with the atmosphere. And that, as I say, there are efforts underway. Part of the problem is lack of observations, and part of the problem is that Antarctica is just so big, it's so huge that you're going to make your computer, you just need so much more resource to do it, and you need to be really clever about how you make your simplifications to make it a tractable problem. But that's how I think that will probably be addressed most. But yeah, sure, it is a problem.
Okay, thank you, Shona. A question from Caroline. Do you think different model parameterizations or empirical values within them could or should even be used for sea ice or the two poles in a single climate model in order to best represent both poles if we understand the sea ice behaves somewhat differently?
Yeah, I think so. I don't think we should necessarily use different model parameterizations, although that might be appropriate, but it feels a bit like giving up. I think if the physics is right, then the model should know what's more important in within. It should be the physics should be self-contained. So although different processes should be important, if those processes are represented well, there's no problem with a process being well represented that isn't important. That's not going to make things bad. So I wouldn't use different parameterizations. Wouldn't use different well, maybe I'm saying that I would. I don't know, but I would possibly use different tuning. So there are, I guess that is different parameterizations. Yeah, I think you would. The problem is that at the moment most of the models are what we call tuned. Is when we basically, it's almost like fitting, but they're tuned to observations, and most of the observations are in the Arctic, and not in the Antarctic. So I mean that's why we don't do so well in the Antarctic. But I don't think we should use different model schemes for the two, but we could possibly use different parameterizations. Yes, okay, yes, I'll go with that.
Okay, thank you, Shona. That seems to be all the questions we have tonight. And no, well done. That was absolutely excellent, and some really fascinating questions there being asked by various people. So I would like to thank you on behalf of the Scottish Centre for your talk tonight. It is really nice to see you again. If you wouldn't mind just holding on until just after we finish, so I can thank you personally for tonight. But as said, on behalf of the Scottish Centre, thank you, and thank you for all the guests who have looked in tonight, and I hope that you have taken something from this. And thank you to all the people who have put questions, really good quality questions, I must say. And I would also like to thank Richard and Vicky behind the scenes from the Scottish Centre, and Eleanor from RMET's HQ for organising the video and making sure everything has been running smoothly behind the scenes tonight. This is our last talk of this season. We will be back in the autumn, and so please look at the RMET's site and the talks that are coming up. It's not just in Scotland. There's talks by quite a number of centres throughout Britain, and all the fascinating speakers and really interesting subjects. So thank everyone again for their participation tonight, and I look forward to seeing you all in the autumn at our next talk. And you will be notified in due course, the speakers and our programme for next year. So thank you, everybody, and a very good night to you all. There's people are logging off now, Shona, but there's still people listening. So, but no, it was absolutely fascinating. And sorry, I referred to South America. What I really meant was New Zealand. I know you were down there, but I picked up David Stevenson's point. Actually, I thought it was really quite interesting about the landmass. And I was looking at it. I was looking at South America there, and that it does. You had a constant grey area, which seemed to be the constant mass, and the sea ice tended to come and go from that. So it's something that you don't actually think about, what defines the landmass on a map or on that. I thought that was really very interesting. That
it is quite interesting, because when you look at, people have done graphics. I think there's one on Google Earth actually, where you can look at Antarctica with the ice removed. So over the continent as well, you can look at what Antarctica would look like without the ice there, and it's quite amazing, because the ice is heavy. There's a lot of ice, so it's pushing the land down. So there's quite a lot of Antarctica that we think of as the land, in the continent, but that's because it's covered in 1 kilometre, 2 kilometres, 3 kilometres at the summit of ice. And if you remove that, you've actually got parts that would be below sea level. So yeah, it is pretty interesting.
Yeah, yeah. Did you actually get onto Antarctica at all? Were you actually out on the ice sheet? No.
No, and it seems to be the story of my life. When I worked with the volcanic ash stuff, I was constantly working with people who were just jetting off to volcanoes all over the place to look at exciting things. And I'd be sitting there in the office with my computer models. And similarly, in New Zealand, everyone seemed to go to Antarctica just like they were going away for the weekend. It didn't seem a big deal at all. And I'd just be in the office on the computer. So no, I didn't get to go. But I have been on sea ice in Greenland a few times. And actually, that is something that I think is really quite important. A lot of people who do this stuff that I was doing, climate modelling and that kind of thing, have never had the opportunity to be involved in the observation side of things. And I think it really helps you understand it a lot more if you get to do both. I think it really helps you sort of know what it physically is that you're modelling, not just what it's supposed to be from the physics, but what it actually looks like. So I think that was quite good. Yeah, but they didn't let me go then.
Yeah. Just I see we've still got a few people logged in and listening to us, but for those who don't know, the other person who's appeared on the screen is Dr. Vicky Ingram, who is my predecessor. She was a chairman before me, and she's been the person doing all the clever stuff behind the scenes to make sure that everybody could get in tonight, ask questions, and the presentation went very smoothly. So thanks also, Vicky. Another successful evening, I think. And
yeah, pleasure. Yeah, there were a couple of questions.
Yeah, thank you very much.
There were a couple of questions coming in really late, and I just thought probably better to finish on time than keep going.
Yeah.
So that's why David Stevenson didn't get his second question. Sorry, David, if you're still on.
All right. I wondered whether David took it down. So I'm watching them as they're coming in, as you were showing them to me. So I didn't realize David had put a supplementary in. So, but I noticed when I was just going to raise it, it was probably out of context by that time. He'd actually been withdrawn. So sorry, David, if you're still there. Apologies for that.
Is it possible for me to see the comments or questions and things, or do they just sort of wipe when we close it?
It will wipe when we close it, I think. I don't think there's a way of copying.
Is there a way that I can look on it just now? How do I do it? It's asking me just now about being a member.
So if you're seeing the polls, you should see something that says chat as well, and if you click on the chat tab,
yeah, chat.
Yeah, you can see everybody's reactions.
So I can oh, that's nice. Yeah. People are so nice.
Yeah, it was. With a person from India, 2 people from Brazil, a person from Ireland, and then spread all over the UK. It's quite fascinating. In the last couple of times, we've had people from France and India and Italy and various parts of Europe and America, South America. So it's really good. We were talking in the committee, Shona, whether we would ever go back to fully meetings in Edinburgh in the lecture theatre at the university. And the feeling is, no, that getting such a large audience, and especially with the quality of speakers like yourself that we always attract, it's good to have a much wider audience. And people, you're sitting in Bergen just now. Our one speaker back was in Calgary. So well, he's actually from Scotland, but he's working for the University of Calgary. But he would have been here in person, but he couldn't move because of COVID. So we didn't lose out because he did it virtually from his house in Calgary, which was it was really good. So it was really good. These generally, I think these talks are actually very positive on this, because we're also getting a lot more interesting questions and more time for questions compared to being in the lecture theatre, where I think some people are a wee bit shy or staid about asking questions, whereas putting them up online is much easier, and getting an answer was good. So yeah.
Yeah, you're much less exposed if you just type it, aren't you? I think yeah, I can see that definitely.
I think we get shorter questions as well online, because when you've got to type it, I think people are more concise in the way they ask it in comparison to when you're in a face-to-face, when you tend to get a lot of observations rather than actual questions, and you get a lot more. I know you get a lot more. Well, my own work has shown type questions in a face-to-face, whereas online it is straight in at the question because they've got to type it.
Yeah. Well, Shona, as you know from being a past committee member, that we would have invited you out to dinner and paid for by the members, not the society. And but just things can't be. Very difficult to do because you're in Bergen also. But how long are you and David out there for?
Oh, well, I don't know. It's a bit of $1 million question. He's so my job here is a permanent job, but my boss is actually in the UK. So I think if I want to keep doing this work, I could probably bring it home with me, I think. But Dave's work has got 2 years left on his contract here. So probably stay for 2 years, I think, and then come home. I think that's kind of the plan.
Yeah, very nice, very nice. Well, again, just thank you very much, and it has been nice seeing you again, Shona, and I hope
yeah, it's nice to see you too. Thanks so much for doing all this. I think it's brilliant. I can't believe these talks are going so well and have turned into this massive thing. When it's brilliant. It's so good to see. I'm so glad that you took it on.
Yeah, well, I don't think you'll be surprised that since you were on the committee, that there's not many people changed, to be honest. We're all about the same. In fact, I think I'm probably the newest of them. Yeah. So yeah, again, thanks, Shona. And next time you're across in your hometown, must have a coffee and catch up with you and Dave and just get the full story about your life over in New Zealand and Bergen. Very exciting.
Yeah, definitely. Well, thanks again very much for having me. That was great. I guess I log off now, but I don't really know how.
You can literally
close the browser.
Close the browser. Brilliant.
Okay.
Thank you very much.
Bye.
Bye. Bye.